And this is your courseware, then the courseware content will be sent to you and maybe made available. I think we have a link also in the chat to edit. Thank you, Alex. Alex has posted for everyone the link as well. Please do make use of the courseware. I think it's going to be very interesting for you as well. And do come up with questions if you have, once you've gone through with it. We encourage you to try the examples exactly. This video is going to be recorded. Maybe you heard Alex saying, once I'm done talking for today, Alex will press the recording button. So you will have also a recording of the sessions. If you have to leave early or anything, there's always going to be a recording about today. Right, and as I mentioned, the feedback session is next week. So please join that as well. We're always happy to see more people. Right, and if there's any question in between, do contact us at this email address as well. Alex, if you can put that email address as well for everyone so that they can reach out if they have questions. All right. Today, our panelists are Dhruv and Lama from our respective offices in New Delhi and Paris, and welcome both. Thank you so much. I'm very excited. I've already heard part of what you've been going to talk about today, and it's very, very intriguing. And with this, I would like to pass on the word to the two of you. And Alex, can you please hit the recording button? I will stop sharing here.
This meeting is being recorded.
I think the recording, yes, has just started. Sorry, Anvanette.
No, go ahead. Welcome, and let's start.
Okay, so thank you everyone for taking the time to join us today for this exciting technical session about teaching control system design with MATLAB and Simulink. I'm not alone here today. I'm joined with my wonderful colleagues. So Dhruv Shindal and myself, we will be doing most of the talking. And for your clarifying questions, we have support from our colleagues, also Akhil Gopinath and Ramana Shori. So please make sure you post your questions in the Q&A functionality to the right-hand side of your screen, and we will be happy to answer your questions as we go along the presentation. These are just a few housekeeping rules, and I think Anvanette did a great job covering most of them. So once again, the Q&A functionality, you can use it to post your questions. You receive the slide files along with the Jump Starter Kit after the webinar via email. And we have, again, just a small reminder about the office hour session scheduled for the May 26th. This is our agenda for today, so we tried to keep it short and simple. I'm going to start off by addressing the challenges that instructors face when teaching control system design. And then Dhruv is going to present a nice set of demos that address these challenges and can help you also solve these challenges when teaching model control systems engineering. But before we dive into the presentation, we are very curious about what you do. So we have two questions for you. I'm going to start by opening the poll. So the first question is, do you teach or plan to teach a control system course in the next semester? So this is just a yes and no question. So you can pick either or. And the second question, what tools are you currently using to teach control systems? This is a multiple choice, so you can choose multiple answers from pencil and paper. Maybe you're already using MATLAB, for instance, and simply you're maybe using another numerical tool to teach control systems. And please feel free to share with us what tools you're currently using, if it's other than MATLAB and Simulink, to teach control systems. So we have still 15 seconds to answer those two polls. I can see the results coming in. Okay. There's still 15 seconds left. Dhruv, just tell me, I know you have extensive experience in teaching control systems in the past. What kind of tools you used to use back then to teach control systems?
Lama. So we would typically start with pen and paper and have the students go over the basic mathematics. And then after that, as we moved on later in the semester, then we would bring in more computational tools, start using a little bit of MATLAB for plotting, and then more of Simulink for building block diagrams. So that's what we want to show today as well.
Okay, great. So I've just shared the poll results. So I think we have 59 already teaching or planning to teach MATLAB and Simulink. So you're in the right place. And what tools are you currently using? We have, I would say, half of our, I would say, participants are using pen and paper. The other half is using MATLAB and Simulink, which is good news. And only 9 out of 140 attendees are using other tools. So I think there's a nice distribution between the classical ways, pen and paper, and the numerical tools. So before we dive into the teaching challenges, let's talk a little bit more about the learning outcomes for any control systems course. And here we're really talking about the basic principles that we usually cover as instructors when talking about control systems. So we talk about learning the process behind the linear time invariant systems, teaching students how they can move from a time domain to frequency domain using Laplace. And again, of course, once we talk about control systems, we have to bring into the picture feedback controllers and the PID controllers. So these are the basic concepts that we usually cover in a course. So to reach these learning outcomes, the instructor is usually faced with different challenges. Today, we're only going to cover 3 of them. So the first challenge would be mainly related to generating interest. So I remember when I was a student, I usually used to question, why do we learn control systems and what kind of real life systems I can apply my knowledge on. And when the instructor usually uses, one example would be using real world example, this can help students project and reflect on their career choices. And here we're just showing renewable energy systems as a starting point for maybe generating interest. Now, the second challenge is related to the learning concepts behind the modeling. And again, this is related to all the equations that we cover and teach in a classical control systems course. So usually students would question, why do I need to calculate a transfer function? Why do I need to move from the time domain to the frequency domain using Laplace transforms? And once the instructor really clarifies and helps the student connect with these concepts, I think then you would have tackled, and also it can help you generate interest in the concept and the course itself. And Dhruv is going to talk more about this, I would say, challenge later on during the presentation. The third and last challenge, of course, the one and only PID controllers. So again, when teaching controls, this is something that will come up. So students need to learn how to design PDI controllers and how to tune them to meet system requirements. So let's just start with the first challenge. As I said previously, a nice way to help students connect with the content is really to give real world examples. And one nice example would be the example of wind turbines. And this is just one example out of tons of examples that you can use with your students. So wind turbines, we usually have 2 control systems. The first control system, it is related to pitch control. Thanks, Drew, for starting the video. So as I said, the first one is related to pitch control, which controls the angle of attack of the blades. The second control system is the nacelle control system, which controls the direction of the nacelle with respect to the winds. You can show your students how a pitch control system works. I'm not going to dig deeper into the pitch control system. I'm going to talk a little bit further about the yaw control system, which is going to show up just right after the pitch control. So here we can see how the nacelle is turning to be perpendicular to the direction of the wind. And this is just one example to show students the idea behind the yield control system. Now let's dig deeper into a real world example. So in a yield control system, you usually need two input parameters. The first input parameter is the wind direction that you can get from the wind vane or the anemometers that are located on the top of the nacelle. And then the second input parameter is the nacelle position, which is basically calculated using the yaw sensor as shown right here. Now the controller will take these inputs, calculate the misalignment between wind position and the nacelle position. And then once we basically reach a certain error value, the controller will trigger the motor and the nacelle will move by a specific number of degrees so that it's perpendicular to the wind position. And again, the whole idea is basically to show students how control systems function in real life and give them just this idea on how and where they can apply their knowledge later on in their careers. So this was just one example, but again, the examples that I shown, it was just a simple video, but behind that, the modeling is very complex. And of course, as an instructor, what you would do necessarily is that you would not start with a very complex, I would say, idea. So the starting point would be a DC motor system, how a DC motor system functions and works, and then move from that to more complex systems. So right now, I'm going to leave the floor to Drew, who's going to take us through a nice set of demos to help you tackle these teaching challenges.
Great. Thanks, Lama. I hope I'm audible, by the way.
You are. I can hear you just fine.
Okay, great. Thanks. So
This meeting is being
it's used in
recorded.
chemical engineering across domains. So it's something that's very widely applicable. That's why we've chosen that example. And what we're going to look at today is how do we develop a mathematical model of a DC motor, and then how do we develop a controller for it? That's the end goal of this entire process. Okay, so how do we derive a transfer function from first principles. Um, what I have here is an example of a DC motor circuit diagram. This is taken from the University of Michigan control tutorials. I would highly recommend you check this out. Um, they've got lots of good demos and examples there which you can draw some inspiration from. So if you look at a typical diagram of a DC motor, you have an electrical part of the circuit. So some voltage is applied and the current flows through the resistance R, the inductance L, and this part here is the DC motor. And then you have a mechanical part in terms of the shaft of the motor on the right-hand side. Um, and what we would typically do is we would look at the position theta, that's the angular position, or the velocity theta dot, and also look at the torque being applied on the system. And maybe we can also apply some viscous friction on the shaft using this variable B. So typically these parameters, this resistance, inductance, friction coefficient, etc., these are things that you can get from a data sheet. And what we've done is we've just put in some example values in this piece of code here. So you can see these 5 lines have a gray background. And this is actually executable code which is present inside the live script. So along with the documentation, you can have the code in the same environment. And if I click on this button at the top, run section, it will actually execute this code. And it's going to behave just like ordinary MATLAB code that will work within the command window or in a script. Okay. So if we look at the first principles of this system, this is essentially a pair of coupled second order differential equations. The first differential equation is the electrical one. So that's voltage V equals K omega plus IR plus LdI over dt. So that's the motor constant. That's the energy dissipated in the resistance, and this part is the inductance. And then we have a second equation, J d omega over dt equals Ki minus d omega. So that term there represents how much energy the current is putting in to turn the shaft. And this is the energy lost due to the friction. And the whole thing is essentially equal to how fast the system is accelerating with respect to the angular inertia, that's J. Now, I hope most of us are able to teach our students the basics of Laplace transforms. And what we want to communicate to them is that we need to switch over from the time domain into the Laplace domain in order to be able to work with these equations, because it's not possible to solve these equations directly in a very easy manner. So when we apply a Laplace transform on these equations, they basically change. So they